Hello, dear student. Very good morning to all of you. I am Dr. Avinash Ulle, Assistant Professor, Sri R. R. Lauti Science College, Morshi. Today we are going to discuss about the NMR spectroscopy. This is our second lecture, and we will continue to our previous one lecture. So from previous lecture, we studied about the principle of NMR spectroscopy. I will try to take a small recap where we studied that this nucleus, every atom has a nucleus which are NMR active. For the NMR active nucleus, the need of atomic mass and mass number, one of them is must be a odd. That time that nucleus is a NMR active. And why this nucleus are NMR active, and we why how it deals with the NMR spectroscopy we already studied. That where we see that nucleus revolving around its own axis, at the same time it has a precessional motion, means this nucleus has a two type of motion. That's why this nucleus act like a tiny bar magnet. And when this tiny bar magnet keep in a presence of external magnetic field, that time it whether it is in alignment with the external magnetic field or it oppose the external magnetic field. And when this nucleus absorb the radio frequency, that time it goes into resonance, and that time when it is in a resonance, it gives the signal, and that signal is called as a NMR spectrum. Like that we seen in our previous lecture. So move on. So next part is a spin-spin coupling. Uh, Generally talking about spin-spin coupling means this is coupling arises due to spin-spin coupling, means the spin of nucleus, right? Spin-spin coupling only occurs between non-equivalent protons on adjacent carbon atom. Means when the nucleus present of different environment or chemical or electronic environment. For that we taken two examples. So we see in this example in 1,2-dichloroethane there is presence of four protons. These four protons have the same chemical and electronic environment. That's why these are the equivalent protons. Means this molecule contains only one set of proton, that all four protons are the equivalent proton. That's why there is no chance to arise the spin-spin coupling, because we've seen that spin-spin coupling only occurs between non-equivalent protons, and there is a presence of only one type of equivalent proton. That's why there is no chance of spin-spin coupling. That's why this gives only one signal, means this molecule contains only one set of proton. That's why it gives only one signal of four proton. But when we're talking about this example in 1,1 dichloroethane, that time we see here this is a one type of proton which is attached to this carbon atom, and these are the three protons which is attached to this adjacent carbon atom. Means the environment of this proton is totally different because it attached to two chloroatom, and the environment of these three protons are different because it attached to only carbon atom. Means these three protons have the same chemical environment as well as electronic environment. That's why these three protons are the equivalent proton. Means this is a one set of proton and this is another set of proton. Means here two set of protons occurs, that is one from one for this proton and one for this proton. Means we are in a state to say said that this spin of this nucleus and spin of this nucleus get coupled. Why? Because they are the different non-equivalent protons. Or we know the spin coupling occurs between the non-equivalent protons, and this one proton and these three protons are the non-equivalent proton. That's why the spin of this nucleus get coupled with the spin of this nucleus. That's why splitting happens. That's why when this proton coupled with these protons, this another set of proton, that time this proton gets split into quartet, because we know the n plus 1 rule, and that in 1 plus 1 rule that tells n means the number of protons there at the adjacent carbon atom. There is a 3 protons at the adjacent carbon atom, means n is equal to 3, and plus 1 means 4, means this nucleus or this proton gives split into quartet and gives a signal. Look at here, this is a quartet, 1 2 3 and 4, means this proton split into quartet. Why this happens? Because there is occurs a spin coupling between the two different or non-equivalent proton, and when these protons are get coupled with this proton, means here also apply n plus 1 rule, means for this proton there is only at the adjacent carbon atom there is only one proton, and n plus 1 rules tell that n is equal to 1, means 1 plus 1 2, and these 3 protons gives split into doublet due to presence of one proton at the adjacent carbon atom. Means we clearly seen here why the spin coupling occurs, and why we got the quartet and why we got the doublet. This is occurs only due to the spin coupling, and a good illustration of this is given by 1H NMR spectra of dichloroethane isomers. Means this is a isomer of dichloroethane, and we can able to distinguish about these two isomers, where the spin coupling occur and where it is not occur. We seen in the this molecule 1,2-dichloroethane there is no occurrence of the spin coupling. Why? Because this molecule contains only one type of proton, and this molecule contains two types of proton. That's why here two types of non-equivalent proton. That's why the spin coupling occurs. Coupling constant. Coupling constant, the distance between the peaks in a given multiplate, is a measure of the splitting effect known as coupling constant. The distance between the peaks in a given multiplate, means we know why this quartet happens, why this signal gets split into quartet due to spin coupling, and why it split into triplet. We look at this example. There is two set of proton, 1 2, means these two protons are the non-equivalent proton, and they are split into due to the environment of adjacent carbon atom. These two protons, set of A proton, get split into quartet by the n plus 1 rule, means there is a presence of 3 proton. That's why n plus 1 rule tells us to about n is equal to 3 and plus 1 means 4. That's why this 2 proton gets split, or set of A proton gets split into quartet, 3 plus 1 4. That's why we can say the this signal or this splitting signal is recorded for the A type of proton or A set of proton, and this B gets split into n plus 1 2 plus 1 3 into triplet. This is a TMS. After that splitting, we look at here multiplates occur, and when we measure the distance between two adjacent peaks in a multiplate, that distance is called as a coupling constant. It's coupling constant, and it denoted by the J and expressed in a hertz. Means coupling constant is a distance between a two adjacent peaks, whether this adjacent peaks or this adjacent peaks or this called as the coupling constant. And always remember that it is expressed in denoted by J and expressed in hertz. It is very useful to identify the adjacent proton where it present. It can be very easy to understand where the protons, where the which protons are nearer to each other. It can be identified by the using of coupling constant. Coupling constant gives the information about the which proton set are adjacent to each other, which are nearer to each other. That information is given by the coupling constant, and that's why this is one of the important phenomena in the 1H NMR spectrum. That's why he said coupling constant are the measure of the effectiveness of spin coupling, and very useful in 1H NMR complex structures. Look at here, this if we taken the triplet, and if we want to calculate the coupling constant, then that time what he did, he just taken a distance between a two adjacent peak in a multiplets and denoted by J and expressed it in a hertz. After that, the next point is factor affecting chemical shift. That are the factors are which are electronegative negativity and inductive effect, hydrogen bonding, van der Waals deshielding, anisotropic effect or space effect. Out of these four, we can going to understand about the electronegativity, inductive effect, and anisotropy effect, which are the factors which are responsible for affecting the chemical shift. So let's start with the electronegativity and inductive effect, how it affect on the chemical shift. Look at this example where we can see clearly this proton. We are studying a 1 NMR spectroscopy, so we are dealing with the proton nucleus, the where its chemical shifts occur, and if it gives a higher Del value or lower Del value, it can be understandable by the effect of electronegative and inductive effect. To this carbon atom, there is a presence of one proton and one chlorine, which is electronegative. That's why it's an electronegative element. That's why it it attracts all the electrons towards itself, and that's why when it acquires abstract electron towards itself, that time this proton feels deshielded. Why it feel deshielded? Because the shielding of electron get decreases due to this electronegative element, because this electronegative element attract the electrons towards itself due to its electronegativity, and that's why this proton get deshielded, means the shielding of electrons get decreases, and that's why we said that proton is a deshielded proton. And the deshielded proton or deshielding proton always gives a Del value at a higher. Deshielded protons appear at downfield, higher Del value, means we can say this proton get deshielded due to electronegativity effect. Chlorine deshielded the proton, that is, it takes valence electron density away from carbon, means the valence electron density takes away from carbon, means the electronegativity of this carbon, it also decreases, because this chlorine, most electronegative, takes electron towards itself, and that's why the effect on this proton nucleus is also observed, and that's why it feels deshielded, and that's why its Del value occurs at a higher Del value, higher chemical shift. This arrow notation shown that if the electronegative effect observed, that time the chemical shift or Del value shifted toward the left hand side, means the values which more occur at the left hand side, it may be affected by the electronegativity effect sometimes. This is a chart of electronegative elements. Look at this fluorine, it attached to this carbon, and these protons are present at this carbon, means these protons get deshielded due to this electronegative elements, where in this three proton gets deshielded by the this oxygen atom, right? And this nucleus also get deshielded due to this electronegative elements, means when the electronegativity increases, the Del value also increases. From fluorine to silicon, the electronegativity get decreases, means look at this electronegative values. For fluorine it is 4, and the rest of these values are here present, and according to its electronegativity value, we can see the chemical shift or Del value for particular protons. Fluorine is the most electronegative element, that's why its chemical shift occurs at 4.26. It is less electronegative than fluorine, that's why its Del value decreases. We can see here here is a decrease in a chemical shift or Del value. Why it it happens? Because the electronegativity of element get decreases, and that's why the del value get decreases. But here we can see it's a most electronegative element, that's why its del value or chemical shift also increases. Anisotropic effect, this is a second effect. In compound containing double bond, triple bond, circulation of 5 electrons about nearby nuclei generate induced field which can either oppose or reinforce the location of proton or the space occupied by the proton. The occurrence of shielding or deshielding can be determined by the location of proton in the space, and so this effect is known as a space effect. Okay, all about this statement we can try to explain by taking an example. If we take on a benzene, if we take on a benzene or any aromatic compound, that time we can see this molecule contains a pi electrons, and anisotropic or space effect is generally observed due to the presence of pi electrons. Means when any molecule possesses a pi electrons, that time it have a pi electrons, right? Means in benzene ring there is a 3 pi bonds, and due to delocalization of this pi electrons there is a generation of current, there is generation of current, and perpendicular to the current there is a generation of magnetic field. Means due to delocalization of pi electrons there is a generation of magnetic field. This is a induced magnetic field. Induced means generated magnetic field due to the pi electrons, right? This is a induced magnetic field. Why this generated? Due to the delocalization of pi electrons, and current is in current here. This is a current, or this is a pi electrons cloud. Okay, and perpendicular to that there is generation of magnetic field, and this magnetic field we can call it as a induced magnetic field, that is B induce. Okay, this magnetic field which is generated here, this induced magnetic field, look at this position. In anisotropic effect we have to focus on the position of particular nucleus. Here a proton, this proton is, look at this proton, this direction of induced magnetic field is a reinforce or in a alignment with the external magnetic field. This also reinforce the direction of this induced magnetic field is with the external magnetic field or in a alignment with the external magnetic field. Okay, and this opposes this direction. Look at this arrow and look at this external magnetic field arrow. It opposes the external magnetic field, where this nucleus reinforces to the external magnetic field. That region is called as a deshielded region. Means this region is a deshielded region, and this region also is a deshielded region, and these protons also at a deshielded region. Means this between benzene rings middle part is in a shielded region, and all the protons are present in a deshielded region. And we know that the deshielded protons always gives a del value or chemical shift at higher del value. At higher del value means at the left hand side, at the maximum at the left hand side in the NMR spectrum. This is benzene ring. This is a deshielded region. This red portion is shown this red portion shows a shielded region. This is a shielded region, and these all protons are deshielded. Deshielded means the electron density is minimum around this nucleus, and electron density where it maximum at the middle portion. That's why this is a shielded portion. And all the protons present in a deshielded region. That's why its chemical shift occurs at 7 to 8 ppm. Means at the left hand side, means del value get increases. Why? Because all these protons are present in a deshielded region, and this is a shielded region. Why we call it as a deshielded region? Because the electron density is minimum around this all nucleus. And why it happens? Due to alignment or oppose of the induced magnetic field. And we can clearly see where the when the alignment of the induced magnetic field is with the external magnetic field, that region is called as a d-shielded region, and all the protons or all the nucleus where which attached to the benzene ring, that all come in a d-shielded region. That's why its del value it's occur about 7 to 8 ppm. Means all the protons of the benzene ring occurs at a d-shielded region, means around 7 to 8 ppm. This is a alkene or vinyl olefinic proton. It occurs at 5 to 6 ppm. It is also maximum. It is also maximum del value, and it occurs at the left hand side. Why it happens? Because look at these protons. These protons come in a de-shielded region, and this is a blue marking region is a shielded region. Why it is shielded? It opposes the external magnetic field, where the protons, the position of protons present where the induced magnetic field is in a alignment with the external magnetic field. That's why these protons come in a de-shielded region, and it occurs at a 5 to 6 ppm del value, and it is maximum. Thank you.